All right, HNO3, nitric acid. If there's one thing that I hate, it's making nitric acid. So it's a necessary evil. You need it mostly for higher end stuff like nitramines, more powerful explosives, HMX, RDX, keto RDX, things like that. I hate high test nitric acid. I hate making it. I hate the amount of time that it takes. It's a huge waste of time. I've broken more glassware over the years making HNO3 than pretty much anything else. So everything else is pretty low, consumption or not expensive. HNO3 is like you're going to be breaking, if you're making HNO3 like gallons and gallons and just running through it, you're going to be breaking all kinds of stuff. You're going to be breaking condensers. You're just going to be breaking lab glass in general. You're going to be having, issues with nitrogen dioxide. There's just a lot of negatives that come along with it. The biggest negative is that it takes a ton of time. I've done it a lot of different ways over the years. I did vacuum distillation for a long time. Vacuum distillation reduces the boiling point so you get less decomposition. It increases the complexity of the operation and the babysitting by about an order of magnitude. You can really get out of control with the vacuum distillation. So as of this year, I've gone back to just doing like this simplistic dummy standard distillation with no vacuum on nitric acid. So this is Glaber's nitric acid production method. And in this method, you're just taking the nitrate salt with the sulfuric acid and producing nitric acid by heating it. It's going to produce high test nitric acid depending on your water content, somewhere between, 93 to 99% on concentration level. You can increase the percentage kind of with diminishing returns by adding additional sulfuric acid. But in general, you just need 1 mole of sulfuric acid to 1 mole of nitrate, salt, and whatever cation of salt you're using, that's going to end up being a bisulfate at the end. If you went additional on the nitrate, like if you did that in excess, then you're going to get sulfate, which is, it's kind of, it's generally not desirable. There's not a whole lot of reasons. So if you wanted to increase the concentration of nitric acid, you would add additional sulfuric acid. But in terms of the actual reaction of producing nitric acid, that's high test. You only need 1 and 1. So I guess let me explain, this is kind of like a long way to get here of lots of trial and error over the years and just deciding on a simple setup. I would consider this simple. So we're using a cheap Weaver heating mantle, 1,000 milliliter. I'm using a 3-neck flask just because that's what I have. Either 3-neck or 2-neck is the best. So it depends on what kind of nitric acid you're making. If you're making one batch, like one and then done, it doesn't really matter what you use. You can use a regular flask. If you're going to be like churning out nitric acid all day, you're gonna have to be reloading this constantly. So in that case, you're not gonna want to have 1 neck. You're gonna want to have at least 2. And the reason why is because you're gonna have to have 1 neck where you can pop off the cap, use like a funnel here, and drop in your reagents to reload it. And then you need another neck that's going to be used for distillation. So this is an offset. I use 2440 joints on everything. There's the most components available for that, and it's the cheapest. So I use an offset. Then I just use an extension piece. This is just tube. It's just for getting distance. So I've got a tube right here, 2440, and then we've got the adapter. The adapter has your thermometer holder up at the top. I wrap this in PTFE. So it's sealed with PTFE tape. I wrap it around there until it's sealed, and then I screw back on this plastic cap. If you don't use PTFE, your plastic's just going to get eaten away pretty much right away. The point that the thermometer should be set to is right at where it passes. This is actually slightly low. That's okay. It's fine. It doesn't make a difference. But you would want it to be about right there because that's where the gas carries over. Then we've got our condenser. This is a really small, simple condenser. I've already broke another condenser doing nitric acid this week, so this is what I'm working with. It looks pretty cold. Then we've got another output adapter going into a 2-neck flask, and I've got a takeoff here, which I need to hook up. So this is my takeoff, and this is going to go to a tube that's going out the window. And this tube is made of PTFE. So it's PTFE tube, I've got it going out the window. That's where the exit gas is gonna go when it starts producing it. For the receiver flask, I've got it in ice water, and I've got the pump, circulating pump for, it's just a cheap circulating pump coming in the bottom, out the top for a condenser. So this chills the receiver vessel, and it's gonna chill the condenser on the same ice water. You can use ice packs. It's kind of like an easy trick to just freeze ice packs and then switch them out as opposed to producing ice and taking up a bunch of room with ice. All right, and then glass joints. So for the glass joints, you want to use sulfuric acid. So what I generally do is just get a beaker and a dropper, and then I'm just gonna pull off one joint, crack it open, and then just needle in some sulfuric acid, and then I just go through the system, do every single joint. And then they're all, when you drop in sulfuric acid, you'll see the joint turn from opaque to clear, and that means you've got a good seal. And then, the only other thing that you want to be careful of is when you're heating this stuff, you don't want to get too out of control so it doesn't produce a bunch of nitrogen dioxide. And the other reason is that, like, especially if you're doing vacuum, you can get totally out of control with foaming, with the boiling point being reduced. And you can shoot hot nitric acid, sulfuric acid foam, like and bisulfate all the way up through the system, and then it will cool when you get it under control. You'll stop the foaming, it'll cool and solidify and harden, and you have to wash up the entire system, because you're gonna have bisulfate contamination. So you don't want that. So make sure that the heating is even and not too intense, and you really judge it from the rate of nitric acid coming out, which should just be a steady, constant drip. So we'll get this going, and I'll show you what that looks like. Okay, at this point we have nitrogen dioxide coming up the adapter here, and we are, in terms of the temperature, we're at about 25 C, still at the still head. So not there yet. We need to evenly heat, and the foam is kind of rising, so I'm gonna actually turn this down a little bit, because that's a little bit aggressive on the foam right away. Okay, so heat has been reduced, but the heat is too high starting off. So this is kind of one of the many joys of producing nitric acid is, dealing with this kind of BS when you're getting a system set up, just getting it tuned just right so that your runs are excellent every time. It's always going to be like this. You're going to overshoot your heat and then have to finesse it and turn it down and just figure it out. And if you don't want to have an overshot heat situation like this, then you're going to have to start with anemic heat and slowly raise the temperature, and it's just gonna, you're gonna add an extra half hour to 45 minutes just to get your temps up, So this is just kind of what you deal with when you're doing nitric acid production. Right now we're at 35 C. Can you see that? Yeah. 37, 38, 39, 40. We're up to 40 C. So temperature has been reduced, but we're kind of getting the hot stuff right now. So this is gonna spike and peak, and then it's gonna reduce back down, and we'll get under control. And then hopefully after this one overshot, starting off, hopefully we get it under control and we get a constant boiling and nitric acid coming over. Okay, so this is what the reaction looks like when it's tamed down a little bit. And we've got lots of foam. So there was headroom on here. This is a 3-neck 1,000 milliliters. So the amount that's used in here, this is 586 grams of sodium nitrate, and then I multiplied that by 1.147 for sulfuric acid, and then I Adjusted that for unknown concentration to around 90%, which is likely what this is, but I'm not really sure. So that amount in the 1 liter vessel gives you enough headroom to where you're rolling like this when your acid's coming out. And we're actually, this isn't even a good rate. Like if you'll notice how slow this drip is, like that's really slow. It's gonna take forever. But that's kind of how it goes if you're not reducing pressure. I would rather go slow and constant and have everything, just steadily putting out nitric acid, as opposed to having systems, have catastrophic failures and crazy stuff going on and having to be really careful about the entire process. I don't like doing that. The reason that I use sodium nitrate is that sodium nitrate is actually denser than potassium nitrate. So you can, get more nitric acid out of a given volume with sodium nitrate. Other nitrates like ammonium nitrate are less desirable because you get side reactions. The double nitrates make kind of strange products. So, in terms of the bisulfates, and it can be a pain, and they're also expensive. So really the only two salts that make any sense are sodium and potassium. Sodium is more advantageous than potassium due to its density. I'm trying to think of what else we should talk about. Maybe some nuances that I do. So on this simple setup here, in the ice bath, I have the return on the condenser just dropping down like that, and that's so that I can always monitor flow, so I can just glance, or in this case, just listen, because that makes like a stream. So I can just hear that the pump is working and functioning. So if it stops working, I can hear it. Another thing to mention is that on your nitrate salt, if you're using potassium or sodium nitrate, in my opinion, it's best to use Prill. And the reason why is because you can monitor the progress of what's going on by looking at the prills. So there are prills floating in here. That means they can't possibly be reacted yet. This is still reacting. This is still going. And so the prills are still formed. They're starting to hollow out, but they're still there. So the reaction isn't complete. Stirring on this isn't even required because you have boiling. You can obviously see how much this material is just moving around in there. So it moves on its own. It doesn't require stirring. And at this point right now, we're coming over at the head at 75C. This is what it looks like. It's a lot less dark red with nitrogen dioxide, and the drip is a little better. It's still kind of slow, but this is just, I'm going to maintain this until that drip slows down a little bit more, and then I'll increase the heat a little bit. All of the discharge line is filling up. It's all going out the window, so everything's working great. There's no NO2 in here. You can't even smell anything. It works, everything's set up and balanced real nice, and we're running smoothly now. This is where, after you get this down, you would want to, take notes, and you should be timing your entire operation so that when you repeat it, you don't have to babysit. You just know when it's going to be done by the time. Other notes on this, like this Sheep Vivor heating mantle here. So I've got a mark. This knob goes much farther than where it's at right now. So you can crank this to where the dial is pointed, all the way down here. So I mark where HNO3 starts. Okay, where it starts HNO3 production. That's where I put that line, and then the low would be where you can get heat to start heating the reaction, but not reach boiling point. So you're not actually producing HNO3. And so like this heating mantle, I pretty much only use for nitric acid. I could use it for anything, but I mark it because it's primarily for nitric acid. That's what's most important here. Now that we're rolling pretty good, we've got, this is our constant drip rate here that we're dealing with. And that's a pretty good rate. It's still, I really like the fast rate of drip that you can get off of a vacuum distillation, but this is fine. No big deal. If you look at how calm this is, we're heating, there's no vacuum. That's how much decomp you have when this thing really gets going. It's not that red, So this is mostly clear. You do have nitrogen dioxide gas in the receiving flask and a little bit through the whole system. It's kind of residual, it's kind of hanging out there, but we're not like, getting crazy decomp the way that we were when we first started this run, figuring out the system. So I would consider this to be smooth with the bubbles there that you see, the amount of foam. I would consider that to be pretty smooth. You kind of want to maintain the way that looks. Maybe even a little bit more foam you could get. You could probably increase the temperature a little bit at this point. But you kind of float around that much foam and that much drip. You know, that drip rate right there, that's about what you want. That foam right there, that's about how much foam you want. If it looks like that, then you're doing good. If your foam is jumping up your offset, that's bad. You need to reduce temperature. If your system is completely red or dark brown gas, that's bad. You need to reduce temperature, too hot. NO2 in the system, so you will get NO2 even under vacuum. The colder that your receiver flask is, the more favored your N2O5 will be. And the hotter it is, the more favored nitrogen dioxide will be. And it'll dissolve into your product. So you'll have dissolved NO2 in your output acid, which gives it, you know, that intense yellow color, or in some cases kind of a reddish color. And that it's still fuming, but you've got dissolved nitrogen dioxide, and that can be removed by pumping oxygen through it. You can also remove it. Sometimes it just equalizes from being cold, like if you store your acid in a freezer, which is what I would recommend. You can knock out the NO2 like that. If you want perfectly clear acid, you want to pump dry oxygen through your finished product. It's a whole separate operation. For nitramines, you can use the yellow acid. You know, pretty much only for novelty will I clear up acid to make it perfect. For all common nitramines, you can just use the fuming nitric acid, somewhere around 98 to 99% that comes off of a standard distillation setup like this. So if you wanted to clear up the nitrogen dioxide out of your acid, what you would do is have a hot plate and acid in a vessel, and you would warm it. You don't want to get too hot. You don't want it fuming a ton, but warming it helps. And then you just stick in a, you know, air bubbler, right? So you're just going to pump air through it. It's got to be dry. So ideally you would have this in silica gel or calcium chloride, something like that. It's not really necessary. If your air is already pretty dry, it'll be okay. The output hose on this is run into a PTFE line, and that's unreactive with nitric acid. So you stick the PTFE line, you stick it in your vessel with your nitric acid and warm, and it's going to clear up your nitric acid and make it perfectly clear. I'm not going to do that for the video because I don't care. I don't want that, and I'm not going to take the time to do that. But I just wanted to demonstrate what a setup would look like to pump in air. You know, this is a very cheap pump, maybe $10 on eBay. Okay, we are now almost an hour into production, thereabouts, and I like the way this is running, so I just wanted to show you. This is a good late stage drip rate. Boom, boom. 1, 1,000, 2, 1,000, 3, 1,000. I think that's pretty good. I like that, or a little bit faster. We can't really get that much faster because we're foaming up a little bit, but it's okay. Every once in a while, it'll kind of, you know, jump up here, and I'll reduce it just slightly, and then it'll come back down. But that's the foam. That's the drip. Looking nice. Very little nitrogen dioxide. This is, you know, it's a clean run, so this is good. So I will repeat this run and time it to get the entire cycle now that I know my positions for heat. And kind of understand, you know, what I'm going to be looking at with this particular glassware setup. I can now repeat it. It's going to be a lot more efficient the second time, and knock out a bunch of nitric acid. My thoughts are that, you know, industrial nitric acid that you can just purchase and pay for is like way better than the stuff that you produce, the high test stuff. I would much rather use industrial azeotropic nitric acid than I would high test. So anytime that you can get away with using the industrial acid, you should do so. That makes me use Petin all the time, because Petin, you don't have to use you know, high test. You can just use industrial. Other thoughts on nitric acid production. You know, this is a setup for a single person producing acid. So we're not anywhere close to industrial production or you know, other methods like conversion of ammonia, which would be much more efficient. This is just for lab production using simple nitrate salts. It can be reproduced everywhere. I think, you should go as cheap as possible and as simple as possible. I think that's the most advantage you can get out of this operation. You know, I'm using a 1 liter flask and a 1 liter mantle, and this collection flask is actually 2 liters. And all these joints are 2440. So this glassware is like the cheapest and most common glassware that you can find. When you break components, you can find new components easily. This is the way to go. And if you wanted to churn out additional acid, you know, beyond what a 1 liter vessel can contain, I would recommend doing multiple setups. So as opposed to, you know, going to a 2 liter or a 4 liter or a 5 liter. In terms of running parallel setups, you know, this is why it's easy to understand, you know, it's kind of easy to see how it would be advantageous to have 10 of these setups running in parallel. The cost of the equipment would be way cheaper than having a 10 liter retort. It'd be way cheaper to just build 10 of these units. All the parts would be interchangeable, so if one unit broke, you could cannibalize the parts and put it into another system. And if you had 10 of these going, you're going to be at a production capacity of somewhere around 1 liter an hour. So you can do 24 liters in a day, which is a lot of high tests, you know, to be producing explosives. And I mean, you can definitely run that in a small space. You know, I mean, you can imagine how large of a space you would need to do, you know, 10 of these. It wouldn't be that large at all. It also folds out nice and compact. I mean, you can pack all this stuff away into a vehicle to move it around or whatever, as opposed to doing something that's 10 times the size, right? You could just use 10 of these all taken apart. So that's definitely the way that I would do it in a guerrilla application. Like if you guys are making nitric, you know, for, you know, guerrilla warfare or whatever, if you're on the front line right now and you need nitric acid for your explosive production, I recommend doing a whole bunch of the cheapest possible 2440 joint systems in parallel, and just have, you know, sets of distillation setups, and then combining all of your acid product at the end to get a ton of high test nitric acid quickly. In terms of storage, you know, I use these amber bottles. I think this is from, who's this from? This is from Carter. This might be a Carter Scientific amber bottle. I don't know. I got this on eBay, but this is the amber bottle that I use to protect the nitric acid from the sun. And I generally only fill it up, you know, one of these I'll only fill up about halfway, and that's for headroom, for pressure. If you have pressure changes, like if you lose temperature in your freezer or something like that, put some headroom in there for the nitric acid to expand and gas off and things like that. Don't fill it all the way up to the top. If you do, you better expect some trouble, because that's probably what you're going to get. Doing it this way, where you're only, you know, filling up about half the bottle, I don't have any trouble with this. I've been storing my acid like this for, you know, years. And the caps, these plastic caps that come with it, they're not even PTFE caps as far as I know. There's just plastic caps, and I don't have any trouble with degradation. The acid being stored in here, in this bottle in particular, is 99%. Okay, so those are the sort of particularities of nitric acid. While I've been talking here, we had some bisulfate rise up the tube, so I just reduced temperature, and now we're kind of going back up as we're just lightly bubbling along, and the temperatures are going back up. And this is kind of just the game that you play when you produce nitric acid. It sucks. I wish I didn't have to do it. I wish I could just buy a high test and it was affordable, but it's not. And I'd have to be crazy I'd have to be using your tax money to be buying that. So it's necessary to produce it in the lab, and it's all, you know, a whole bundle of joy that you can have producing nitric acid. Okay, so we are now 2 hours in to distillation, and this is what our progress looks like. The temperature, we are now at the head, we are now moving at about 94, 95 C, somewhere around there. We've got an okay rate. The whole system's, you know, really nice and clear at this point, right? And this is, you know, like we're beyond halfway now. And we're just gonna keep on going. We could add additional materials if we wanted to at this point. I'm doing a time check, so I'm going to take this all the way down. Okay, so now we're towards the end. We are still producing and dropping nitric acid. Right now, the still temperature, we're at 95 C. And I've covered with an aluminum foil. This holds heat in and makes it more consistent. It's a good idea to do this from the very beginning, but you can't see what's going on in here if I do this from the beginning. So to squeeze out the last few drops, we've got this insulated now with aluminum foil. Okay, so this is our in state. We are now doing a drip of once every 4 to 6 seconds, and we're at about 117, and so this is done. This is what it looks like when it's done. We've squeezed mostly all the nitric acid that we're going to get out of here. We've squeezed out of that, so we are going to wrap this one up. Okay, we are on the second batch, running here pretty smoothly this time. The heating cycle, I noticed, is over an hour on this device, on this heating device. So you get an hour to get to the reaction starting, and then I'm doing a second timing, but it's generally about a 3-hour run time for the reaction to take place. Your output for the quantity that was in there is going to be somewhere around 300 milliliters. I haven't measured it, but it's based off of 586 grams of sodium nitrate and 746.8 grams of 90% sulfuric acid. You're getting 300 milliliters of concentrated acid. So with this smooth run, with everything worked out, we still get at a modest temperature. We just get spikes in bubbling here, where you're getting the bisulfate shooting up the offset adapter. So that's not good. I'm kind of watching it to see if it subsides on its own. If it gets past the adapter, I'm going to reduce heat. We'll see what happens. But this is just how it goes when you're making HNO3. You just kind of got to babysit a little bit. So this is kind of the, a log that I would use to track production every time I change a piece of equipment. So this combination of equipment is all new because I broke some condensers, so it changes. I mean, this is a different size, so it sort of changes everything. So this is my log. It's, what's in there, start, and then we've got the first drip right here. So this lets me track everything that's going on. So we've got about an hour and 8 minutes from the start, which is exactly 1630 to 1738. That's just to get it going, and then we're going to continue on 3 hours, and then we'll be done. We should have around 300 milliliters in yield. Okay, we are now into the next day. We're continuing these batches, and we've got it pretty dialed in. The temps, in terms of startup temp, going from cold to first drop on the still, we've got that down to exactly 25 minutes. So that's been reduced a little bit more than half to save some time by cranking the heat initially and then pulling the heat down when we start getting red gas coming through the system. So the total time with this setup on this type of run, you're gonna have 25 minutes to get the first drop, and then you're gonna have a 3-hour reaction time that can go all the way up to 3.5 hours. It depends on how much water you want in your end product. If you wanted a low water content and high concentration nitric acid, 99%, you're gonna wanna pull it off before it gets to about 90 C. If you don't care about the water and you just wanna squeeze out all of the nitric acid possible from a batch, like if you're gonna go back through and reconcentrate it afterward, then you would wanna go all the way up into 120 C, pull out all the nitric acid, and then you'll pull over some additional water too. So as it is right now, the last batch from last night, 381.9 was the yield. The total distillation time was 3.5 hours, almost exactly. In terms of the molar yield of acid, you're getting somewhere around the 87% range of theory. If I ran the reaction longer and pulled over more water, that would obviously increase, along with pulling over additional water.